Okay, welcome to again the second order low pass RC low pass filter. So let us continue that discussion what we had earlier in the previous video. We will change the gain of the entire circuit from 1.56 to a different gain, and then we'll make it less than 1.56 and more than 1.56 and see the pore flatness and the overshoot response. So this is what we observed in the previous video. We could able to have a gain of 1.56, and you can see it was almost flat response. So let us again go back to the 20 sim, and then try to give a gain of 2.5. If the gain is 2.5, as per this equation, for a value of 1 over RC of 1000, we're going to end up with this as a transfer function. If I edit this transfer function, I have to get a overshoot response. So let us go to 20 sim and then try to find out, try to edit the same transfer function. So here we are supposed to have a transfer function whose, let us go back to this and try to see what is the expression here. Let us go back to previous slide. You can see we have a gain of 2.5 which corresponds to 250 followed by 4 zeros. Let me edit this. So this is 250 1 2 3 4 and then this happens to be 500, yes, because we have this is a square 500s and this is 1000. Okay, this actually corresponds to an overshoot response which will have a gain of 2.5 which is more than 1.56, which will result in a value of Q which is more than 0.707. It should certainly end up with an overshoot response. So let us see the response of the circuit now. Let me apply, okay, let me see, okay. So let me see the pole 0 position. So you can see poles have come closer to imaged axis, and let me see the Bode plot of this. We should have an overshoot response. You can see there's an overshoot response. You can see the magnitude plot has got an overshoot here. So this is flat here. Now you can see this is the overshoot. So this overshoot response is due to a larger gain which is more than 1.56. So this is how we can able to see the value of A, which is related to the quality factor. As the pole quality changes, we're going to have a overshoot response. In the previous case, when the gain was equal to 1.56, we could able to get a maximally flat response, and this is for a gain which is more than 1.56. So we'll just go to again the slides and try to find out. For a poor response, the value of A will be AB will be 1.1. If the gain of the amplifier is 1.1, which is less than 1.56, the response will not be flat for a larger frequency. This will have a poor flat response. That's why it is written as poor response here. So let me just again edit the same transfer function what we had. So let us go to 20 sim again and then try to edit the transfer function. Now it is no more. So this will be actually 1 1. This will be 1 1, and this happens to be. So if you can see the equation, let me see the equation, try to find out. This is actually 1900. This is actually 3 minus AP, because the gain of the amplifier is 1.1. 3 minus 1.1 is 1.9 into 1000, which is 1900. So let me just edit this to 1900, and this is also fine here. This is okay. AV is fine. If we see it now, so it will not have an overshoot response, but the response will not be flat for a larger frequency. So let me see the pole 0 plot. You can see pole 0 plot is too far away from the imaged axis. Now you can see it's far away from the imaged axis, and it was very close to imaged axis when the AV was greater than 1.56. When it was 1.56, it was there in the midway. So let us see the Bode plot of this. You can see this is a Bode plot what I have. So this is the Bode plot response of. So here we have the Bode plot. If you can see here this is not flatter up to suppose if you see the magnitude of this, suppose if you change this, so when it is equal to if you can see here when it is 1000, it is not close to minus 3 dB. Actually what is the DC gain? DC gain happens to be 0.8 dB, almost close to 1 dB. So if it is at minus 3 dB, if it was maximally flat, it was there at exactly minus 3 dB of this is, so it would have been minus 2. So since it is not maximally flat, so if I can see here, if I can move this and then put it at 1000 radian per second, you can see now it is almost down by almost 4 dB, minus 4 dB. So this way, of course, it is now not minus 4 dB, it's more than minus 5.6 dB, because it was there plus 0.8, it has become minus 4.8. So overall difference from here to here is almost minus 5.6. So this shows that this is not a maximally flat response. We'll get a maximally flat response only when the value of AV is equal to 1.56. So at that point, when this is exactly 3 dB down from this point, this will be 1000. So we will observe the similar type of variations in case of LT spice. So let us go to LT spice and try to see the circuit. So this is a LT spice circuit. You can see here we have rigged up the same circuit what we shown earlier. You can see this is your RC to RC networks, so having a similar circuit, and you can see this is a resistor whose value can be varied. We have used a sweeping parameter that is called as dot step param. This parameter which has got a value of RVR, we are changing from 586 ohm to 1500 ohm and then 100 ohm. So when it is 586, this corresponds to a gain of 1.56. When this is equal to 1500, this corresponds to gain of 2.5. When it is 100, it corresponds to gain of 1.1. So we're going to see all the three plots in a single border plot. So let me run this and show you how does the plot looks like. Okay, this is the frequency response of this particular circuit. Let me just see the output here. So this is the frequency response. So since we are sweeping a parameter of RF for three values simultaneously, you can see the blue one corresponds to maximally flat response. You can see it is flatter to a larger extent. This is poor flat response. This corresponds to overshoot response. So the red one corresponds to a gain of more than 1.56, which is in this case 2.5. The blue one exactly a voltage gain of 1.56. So that's why you have a maximally flat response. And this corresponds to a gain of 1.1. That's why you don't have a flatness for a larger value, larger frequency. Of course, since the value of R and C happens to be 1 kilo ohm and 0.1 microfarad, the cutoff frequency of this circuit is actually 1.59 kilohertz, which you can see for this. You can see now when I just move this, I'll just put it on. So let me just move this. Let me see what is the gain of this. Here you can see the DC gain of 1 second. Let me know the DC gain of this. So DC gain is almost, if you can see, it's almost 4 dB. So which is 20 log of 1.56, almost 4 dB. You can see 4 dB minus 3 will be equal to 1 dB. You can see when the magnitude becomes 1 dB, the cutoff frequency is close to 1.59 kilohertz. So we are actually looking at this as 1 dB and the corresponding frequency is cutoff frequency. I am going to 1 dB because 4 minus 3 dB happens to be 1 dB. So now you are there close to that 1 dB point. You can see this is very close to 1 dB, which is almost 0.955 dB or 955 milli happens to be 1 dB. So this actually corresponds to 3 dB difference from this DC point to this. You can see at that point the frequency is exactly 1.59 kHz or 1.6 kHz. This shows that this is having a maximally flat response. Suppose if you come to this poor response circuit, if you can see now the gain is almost 1 dB. So, and then coming down to 3 dB down, that is because 1 minus 3 happens to be 2 dB or minus 2 dB. You can see, just have a look at this. Let me have a look at this. This is actually 820 or 0.8 dB. You are looking for minus 2.2 dB. So this is actually the cutoff frequency. Cutoff frequency is actually 1.12, whereas the expected cutoff frequency is 1.59 kHz. So 1.59 kHz is the expected frequency, whereas you can see you're getting the almost same frequency for a maximally flat. So that's why the blue one, which corresponds to a gain of 1.56, has got maximal flat response. That's why we call this gain, which corresponds to a Q of 0.707, happens to be a maximally flat response. For a gain more than 1.56, you can certainly see there is a overshoot response, which is not good for many applications. So in case of Butterworth second order filter, for a gain of 1.56, we're going to get maximally flat response. That's what we have seen in this particular. Let me see here. So this is what we saw. So for less than 1.6 we had a poor response. For 1.56 it is maximally flat. For a gain which was 2.5 in our case, there was an overshoot. So any gain more than 1.56 we have an overshoot. Hope you enjoyed seeing this analysis of Bode plot for a second order low pass filter by changing the gain and seeing how does the flatness of the frequency response of the low pass filter will change depending on the value of AV, because this value of AV will change the value of Q. As the value of Q changes, the pole position changes. If pole position changes, naturally the frequency response will be slightly different and it will be overshoot for values more than 1.56. Thank you.